Alright guys, so we are diving into chapter 5 today in this video, and title of chapter 5 is called the definite integral. Okay, so we've just wrapped up our whole lesson on derivatives and applications of derivatives, and now we are diving into what is called the definite integral. And so kind of a preface into this video is that this is going to be a very introductory video. There might might be a little bit more saying than doing in this video, but it just kind of gives us a little bit more of an insight as to why are we about to spend the time talking about integrals, okay? And so that's kind of really the purpose of this first video is. 5.1 as a whole, estimating with finite sums, our goals are going to be able to estimate the distances traveled and finding some areas under a curve by using what we call the rectangular approximation method. Okay, that's in a little bit. Let's kind of first talk for a second as to what are integrals and why are we actually going to spend some time looking into them. Well, at some point, obviously, there was a need to calculate the instantaneous rates of change, okay? And that's what we did, all right, as mathematicians. I don't say we as in I invented it, but as mathematicians, that is what was happening when they invented derivatives, a way to start talking about instantaneous rates of change, okay? And that led to the discoverers of calculus, to an investigation of the slopes of the tangent line, and then ultimately, obviously, we arrived at the derivative when it was all said and done. And when we're dealing with derivatives, we call it a differential calculus. All right, we call it, that's how we name it when we're talking about derivatives, differential calculus. But the thing about the derivatives is it was only part of the big picture. Okay, it was only part of the big picture because we started having to think to ourselves, well, there's more there's more to it than just finding an instantaneous rate of change. Okay, it we needed to describe how functions change at any given instant, and then they needed a method to just kind of describe how those changes could accumulate over a given interval, okay? So it was kind of like, all right, we found this derivative, and then we said at a given point the instantaneous rate of change is blank. But then we kind of need to start thinking, well, what about the instant rate of change over a certain interval, a certain amount of time that is happening? There has to be some kind of connection between the instantaneous rate of change at a specific spot and then kind of compare it to the instantaneous rate of change over a variety of spots, all right, or over a given interval or a given, I don't know, time frame, for depending on what the situation is that we're kind of talking about. And so this led us to start thinking about a topic that we know as the area under a curve, okay? Area under a curve. And we're going to talk about that here in a second, but that's really what it is. It's the area under a curve. And that kind of shows the relationship between the instantaneous rate of change at, x sub 0, and then as it continues to go to x sub 0 plus 1, and x sub 0 plus 2, and x sub 0 plus 3, and so on and so forth. Okay? And that is really how the thought of what we call integral calculus came into play. Okay? Is finding the relationship past the instantaneous rate of change, but the instantaneous rate of change over a given amount of time or over a certain interval that we are going to be looking at. Okay? So what I want us to do to start some things on off and kind of putting some more things into understanding is I want you to consider the following problem. Okay? It's a very simple problem that we have seen since we've been in grade school. Okay? So the train moves along a track at a steady rate of 75 miles an hour from 7 a.m. to 9 a.m. It says, what is the total distance traveled? I mean, think back to maybe early middle school. You might have even talked a little bit about it, if you're in advanced in, elementary school a little bit. But this is just the basic use of the distance formula, right? This is just distance in this case So this is just going to be distance equals rate times time, right? So this is just distance equals rate times time. Okay, that's all this really is looking into. And so it's basically saying, well, how far did you travel if you went 75 miles an hour for 2 hours? Well, in this case, that's going to be 75 multiplied by 2, or then we see in the end, the distance traveled is 150 miles. Okay? So what you see to the left over here is a graph that represents this situation. Okay? You start at 7 a.m., all right? So here's where the starting point is, at 7. You finish at 9, right? So you start at 7, you finish at 9. The total time was 2 hours, right? So it took 2 hours to get there. And over this time frame, you steadily traveled 75 miles an hour, okay? And so think about what's happening here. The total distance traveled was 150 miles an hour. It's not a coincidence that the area of this box that I've drawn is 150. The area under this steady curve right here, all right, is 75 for our height multiplied, so 75 for our height, multiplied by 2 for our base, all right? So there's just base times height. And so, like I said, that's not a coincidence, all right? That really is what integrals are all about, is finding the area underneath this particular curve. The thing that makes this an easy problem for us is the fact that you are going 75 miles an hour from start to finish. You don't go a little bit less, you don't go a little bit more. You constantly are at 75 miles an hour. So the point of integral we'll start getting into is, well, let's say for instance, we unfortunately don't have such an easy situation. What happens if we start at a random point A, finish at a random point B, and again, this is time versus velocity. Okay, so this is time versus velocity. And let's say, for instance, it just kind of starts looking something more like this. That curve is not steady. And so it's now we're starting to ask us the questions as to why, how, where do we go about this? This is not just finding this area. Because if I drop down from here and drop down from here, and I still want to find the area under this curve, well, that's not just base times height anymore. And that's where the thought of integrals start getting into play. Now we're starting to think, okay, there's got to be a way to find the area from A to B, even though this is not a steady movement or velocity the entire time on through. And so what we are going to start looking into is an approximation or an estimation in this section. And what we're going to start taking this as is, well, what if I could make some easier figures underneath this curve, like a square or a rectangle, in order to find an approximation for the area under the curve. And we're going to dive in our next video with an example. And let's say, for instance, we kind of use that same thing here. Let's say that we could possibly find a bunch of partitioned rectangles that we know is just base times height as we go through. And if we find enough of these rectangles, we can come to a pretty good representation or a pretty good approximation of what the area under the curve is going to be. And that is what the main goal of this section is going to be about, is the approximating it underneath the curve. But in time, we are not going to be approximating anymore, and we'll get to integrals, and we're going to be able to, in fact, know for sure, and it's not going to be an approximation anymore. Before we get there, we got to get a little bit of an insight as to where this all stems from, okay? So that's going to wrap it up for this video. Like I said, this is our introductory to Chapter 5 video. In our next video, we are diving into an example
as defined in distance traveled when the velocity varies itself.